All right. So the work done is given by W equals Fs. Okay, tell me the work done is a vector quantity or scalar quantity? Okay, what about Hirosh? Is it a vector quantity or scalar quantity? Okay, the work done is a scalar quantity because work done is energy. Energy and work done are scalar, right? So here the force is a vector quantity, displacement is a vector quantity, and actually here we have the dot product between the force and the displacement. So we have studied in vectors lesson, it will produce a scalar, right? So here work done is a scalar, okay? All right. And the dimension ml squared t minus 2. And now let's say the force is acting at an angle, okay? So in that case, okay, so if the force is acting at an angle like this, so we are making angle, let's say theta with the horizontal. Okay, in that case, the work done is given by F cos theta into X. Okay, so the work done is given by W equals Fs cos theta. Okay, so you can write if the force is acting uh, if the force is acting at an angle. So you can write, no need to write all this. Force which makes an angle theta with the horizontal, work done is given by W equals Fs cos theta. Okay, I will show you how this will come and show the derivation. So it is actually the dot product between force and the displacement, but in physics we don't discuss about it is either dot product or cross product. We don't discuss anything like that. So if the force acting along the direction of the displacement, simply work done is force into S. But if there is an angle between them, then you take the angle theta. So that one I can explain you like this. Let's say this horizontal ground and there is a box, something like this. And let's say the force is applied at an angle theta. So we can take this angle to be, okay, so let's say F, okay. And let's say that this box is moved to a displacement of S, okay. So in definition what we wrote, the work done by a force is the product of force and the displacement in the direction of the force, okay. So here work done by a force is the product of, okay. Actually this note I didn't make actually. Like a couple of days ago, I asked one of my students to prepare a note for me because I haven't done a note for work done. But anyway, yeah, so if there's any typing mistakes, please excuse it. All right. And also, I didn't get a time to go through this. All right, so here we can resolve this into two perpendicular components. So one is in the direction horizontal and one is in the direction of vertical direction and horizontal direction. You can resolve. So this one is f cos theta and this is f sin theta. Okay. So this f sin theta component is perpendicular to the direction of the motion, so it doesn't do any work. So this component f sin theta is perpendicular to the direction of motion, so it doesn't do any work. But this f cos theta makes a work. So therefore work done we can write now the force is f cos theta. Okay. So f cos theta into the displacement is w. So then you get w equals fs cos theta. Okay. All right. Now for example, if you remember the dot product, f vector dot s vector, that is actually the modulus of magnitude of f times magnitude of s times cos theta. Okay, but then again I'm saying we don't discuss anything about dot products in physics. Okay, so then that is the work done. Okay, or else without resolving, we can also do like this. I mean, without resolving the force, let's say this object has moved to such distance, such a displacement. What I can do is I can construct this right angle triangle. So it has to be start from, wait, let me, okay, so here I draw, so I have to draw a line starting from the, initial portion of the displacement. Okay, so this is the initial portion. From there, I have to draw a line. It should be parallel to the force. Okay, I can't draw like that. It has to be parallel, not through the force also. Okay, it has to be a parallel line. So I draw a parallel line to the F. So this is the force. For the force, I draw a parallel line. Okay, and then I complete this right angle triangle. Okay, from here I complete the right angle triangle. So then let's say this angle is 90. So 90. So then what will be this distance? I mean this length or the displacement, this one. So that length we can find using the trigonometry. So this angle is theta, therefore s cos theta. This length will be s cos theta. Because this is theta, this angle theta, this hypotenuse. So towards the angle cos, therefore this will be s cos theta. Then if you consider the work done W along this direction, the force is F and the displacement here is s cos theta. So in that way also you get same Fs cos theta. Okay. All right. Is that clear, guys? Is it clear? Please let me know. You can drop a text in the chat box or you can unmute and talk. Okay, sure. So here, now this is the displacement. Okay. So you consider the initial point of the displacement and draw a parallel line to the F, to the force. Okay, whatever the force is acting on it, you have to draw a parallel line to the force. Okay, so then you extend that line. Okay, so this is the line parallel to the force starting from the initial point. And then from the ending point, so this is the final point, you complete the right angle triangle. Okay, you complete right angle triangle. So this length is S, right? This length is S, then we can find this length, no? In this right angle triangle. So that length will be what? So since this is S, this length will be what? It will be S cos theta, right? Or else you can take this as X. So cos theta, if you write, cos theta is equals adjacent X over hypotenuse S. So X equals S cos theta. So therefore, the displacement in the direction of the force is s cos theta. Therefore, again, F into s cos theta will come. Abhiushan, is it clear now? All right. F sine theta, we don't have to consider now. Now, there are two things. First, you can resolve it. Okay, you resolve this. Okay, when you resolve, then you have instead of f, you have these two components. So you have no motion in the f sine theta direction. So therefore, it doesn't do any work. If a work is happening, means there should be a movement in that direction. So since there is no any motion in the vertical direction, there is no work done by the f sine theta component. But by the f cos theta component, there is a work done. So that is equals to f cos theta. Now the next one, instead of resolving, you can directly consider this direction force. I mean, now you don't have to consider these two components. Now instead of these two, I mean, you have the same original force, right? F. So that F into the displacement in that direction is, so that is x is s cos theta. So therefore W equals capital F into s cos theta. Hirosh, did you understand? Okay. So if you want, you can note down this. That is not so important, but you have to get the idea and the concept. Okay. So the important thing is, if a force is directly acting in the direction of the displacement, then work done is F into S. But if there is an angle between the force and the displacement, then W equals Fs cos theta. Okay. All right. Okay. A work is done by a force only when there is a motion. Okay. Now, for example, let's say there is a horizontal wall. Okay. So here's a horizontal wall and this ground. And let's keep a box. Let's say there is a box here. And then you are applying a force F. Okay. Applying for longer time. But there is no any motion. Okay. But there is no any motion. Okay. So therefore, there is no work done. So here S is 0, delta S 0. Okay, change in displacement is 0, therefore work done is 0. Okay. If certain force acts perpendicular to direction of motion, perpendicular to the direction of motion, there is no work done by that force, right? Now, for example, in the previous one, I mean, we discussed that when this is force is acting at an angle, theta, then we can resolve into two components. Okay. So one component f cos theta, and then this vertical component f sine theta. So let's say the object is moving only in the horizontal direction. So there is no work done by this perpendicular component. Okay. All right. Okay. So now we know what is work done. Okay. Okay. Now, for example, a force of 1 Newton required to raise an object of weight 1 Newton steadily. If it's raised by 1 meter, the work done by the force is 1 joule. Okay, 1 Newton meter. Okay, sure. Okay, so then the next one, the energy. Okay, so the force was displacement of. Okay, so here, uh, okay, you can put a small heading. Resultant force was displacement graph. Okay, so you are plotting a graph of the resultant force against the displacement. Okay, so F and then displacement is. Let's say this is the variation of force and the displacement. Work done. Okay, so this area will gives you the work done. We can put a note. So area of force versus displacement graph is equal to work done. Okay, so then write down the topic energy. Okay, raise your hand if you finish drawing that graph. Okay, so write down the topic energy. And then write down energy is the ability to do work. The energy is the ability to do work. Energy is the ability to do work. Okay, so there are various types of energy: kinetic energy, gravitation potential energy, electrostatic potential energy, electrical energy, sound energy, thermal energy, nuclear energy, light energy, or as photon energy, chemical energy, etc. Even more uh, binding energy, more energies are there. Okay, so here in this lesson, mainly we will be discussing the kinetic energy and gravitation potential energy, as well as we will be studying elastic potential energy as well. So under in this list, you can mention elastic potential energy. Okay, so write down the topic kinetic energy. Kinetic energy. Okay, let's say we have a box object. Applied force F. Let's say initial velocity is 0. So U equals 0. Mass is M. And then it has experienced A acceleration. So by applying F, so according to F equals ma, it will gain some acceleration. So after some time, let's say this object has a velocity v. Okay. So the displacement covered during this time gap, let's take it as S. So S is the displacement of the object within some time. Let's say t equals t. All right. So here we want to find the work done. So the work done is we know W equals force into displacement. Since force and the displacement are in the same direction, we can straight away multiply force into displacement. Okay, so here I find the force. To find force, we can write use Newton's second law. Okay, using Newton's second law of motion. So in this direction, I can write F equals ma. So therefore, A equals F over m. So the direction of the acceleration is the same as the direction of the force. All right. Sorry, no need to subject. No need to subject A. I keep it as F equals and F equals ma. Okay. So then next thing, I'm going to find the displacement. So for that, I can use in this direction, v squared is equals to u squared plus 2as. So the final velocity is v squared is equal to u initial velocity is 0 plus 2 into a into s. So therefore, s equals to v squared over 2a. So this is equation 1 and this is 2 and this is 3. So I can combine or use from 1, 2 and 3. I have W is equals to force MA times S is V squared over 2A. So A and A cancel. Therefore, we get W equals half M V squared. So that is the work done. So it's the work done. Work done is equals half mv squared. Okay. So here we want to find the kinetic energy. Before that, we will discuss something called work energy principle. Work energy principle. Work energy. Okay, work energy principle. Okay, do you know what is work energy principle? What is work energy principle? You can unmute, and I think you may have studied this in your OLS. Have you? Have you studied work energy principle? Can't remember. Okay, all right. No. Okay. So the work energy principle says when you do some work that the equivalent amount of energy uh, will transfer from one form to another form. Now, for example, I don't know, wait, hold on. Okay. So, for example, let's say this is on a table or ground. If I want to lift this, okay. So, if I want to lift this, I have to do work. Okay, I have to do work against the gravity. The gravitational force between this object and the earth. The earth pushes the object downward, but I have to do work against that. Okay, so when I do work against that, okay, I'm doing work. If a person is doing work, the equivalent amount of energy will be released. I mean, so if I lift this, okay, to some height, so the energy difference you can find using mgh. That's our next topic, the potential energy. Okay, so that equivalent amount of energy I lose. Okay, because I have some kinetic energy. So when I'm doing that work, that kinetic energy is transferring or converting into potential energy. So the work energy principle says when a work is done on an object, okay, the energy will transfer from one form to another form. So here what happens, my chemical energy is transferring to gravitational potential energy. That is one way of saying work energy principle. Or else the other way of saying is when a person does a work, the uh, energy is decreases, and when the work is done on now, for example, let's say an object, okay, when the work is done by the object, its energy decreases, or when the work is done on the object, its energy increases. Okay, now for example, if I lift this, I'm doing work on this object, so its gravitation potential energy increases. Okay, now, or else I can simply take the gravity. Now, for example, now here I'm doing work against the gravity. Okay, I'm doing work against the gravity. So then here gravitation potential energy increased. It has been stored. So if I release this, the gravity do the work. So its energy will be decreases. Is that clear? Is that clear, guys? Okay. Okay, I'll give you nicely, sentence for work energy principle. Maybe I can use my friend's help, the ChatGPT. Okay, so here the work energy principle is given only for the kinetic energy. The work states that the work done on an object is equal to the change in its kinetic energy. So we can write in most general way. So I think I can get it. No. Okay, so here this is hold on. Okay. You can write down this because it's actually, if you consider all the scenario, the kinetic energy only increasing. Now, for example, if you take an object and release, the gravitation field does the work. So that work done is converting into kinetic energy. Or for example, you can consider a spring, okay, and released the, or maybe arrow, okay. The elastic, if you release your hand, the elastic potential energy will converts into kinetic energy. You can consider a spring also. For in spring, there also what happens, the elastic potential energy again converts into kinetic energy. So you can state this, the work done by the net force acting on an object is equal to change in its kinetic energy. So that is the work energy principle. Now for example, here I take this, okay, I'm doing work. What happens? My chemical energy converts into kinetic energy. Okay. So you had right under the work energy principle. Okay. So then can come back here. So then we can write that statement as a formula that W, the work done, is equals to W equals to change in kinetic energy. Let's say delta E K, kinetic energy. So then therefore W equals the final energy, let's say the final energy, let's mark it as E. Okay, so here I can write EF, the final energy, final kinetic energy is E, and EI in the initially it is at rest. So you can see there is no kinetic energy, 0. So therefore the change in kinetic energy will be EF minus EI. So W equals E minus 0 E. So therefore the energy is equals to W. The energy is equals to work done. So after that you can write the energy is equals to half mv squared. Okay. Yeah, I wrote. Can you see the screen? But nothing new. Hold on. Yeah. Okay. For me also, it's not appearing to me. Okay. So I rewrite that. Okay. Mm, nothing is. Yeah. Hold on. Okay. Maybe I can stop share. I think there's an issue with the screen sharing. Okay. Now I think it will appear to you. Yeah. Okay. Somehow the screen sharing has got paused. Okay, I'll explain here. So according to work energy principle, the work done is equals to change in kinetic energy. Work done is equals to change in kinetic energy. Okay, and therefore we can write the change, we write always final state minus initial state. So the final energy is E. Let's say the final kinetic energy is E, and initial energies, you can see initially the velocity is 0. So it will be 0. Initial kinetic energy 0. So therefore work done is EF minus EI. EF is E minus 0. You get the same thing. So therefore energy is equals to work done. Right. So work done is half mv squared. Therefore energy is equals to half mv squared. Okay, and then potential energy. Okay, potential energy. Now let's say an object is on the ground. Okay, and let's say it has mass m, and you're lifting to some height. Okay, The kinetic energy definition, there is no definition to write. So if you want to write the definition, it will be what we can state is the I mean swabhava, the type of energy that is when an object has a movement. Okay, that's what how we can say. But in exam, you won't get a question what is kinetic energy means. But it's like if you want, we can get something like we can say something like the energy that related to the motion of a body or object. Let's see what this AI gives. The type of energy that is comes with the motion of an object. What is kinetic energy? Is the energy possessed by an object due to its motion. That's all we can say. Yeah. The type of energy gained due to its motion. Any object has a mass and moving with certain velocity has kinetic energy. It's given by half mv squared. Okay. Okay, and then the potential energy. So let's say the potential energy here. Okay, so let's say there is object and we have lifted that to a height of let's say h. Oops. Okay, h. So then the energy we can find that is actually again we can use the work energy principle, or else simply we can write the work done is the work done equals force times the displacement. So here the force, if I want to lift an object, if I want to lift this, I want to apply a force that is greater than its weight, right? If I want to lift an object means, now for example, let's say you have a 10 kilogram of 10 kilogram of this price and its weight is 100 Newton. So you need to apply a force of 100 Newton minimum to lift that. Okay. So if you apply 80 Newton, you won't be able to lift. Okay. If you apply 120 Newton, you can lift. So minimum, you have to apply a force that is equal to its weight. So we can take force mg into the displacement h. Okay. So W equals mgh. Now here, for example, you can see this object is in my hand. So that is at some height. And then I'm lifting that. So in that case, so the work done is equals normal reaction force. I'm acting the normal reaction force times the displacement h. So you can see since initially it is at equilibrium, So, or else if I move this with constant velocity, okay, then R will be equals to mg. Therefore, W equals mgh again. Okay. So therefore, the work done is mgh, and then according to work energy principle, this work done is equals to the energy stored here. Okay, so then we can write E equals energy equals mgh. Okay, what if I ask you, for example, let's say this point is A, this location B. What is the gravitational potential energy of the object at A? What is the gravitational potential energy of the object at point A? Say, okay, I expected that. Good. How about Abhishani? Yeah, it's not correct. How about Abhishani? Can you come up with any answer? It's okay to be wrong because we are learning. The question is, what is the gravitational potential energy of the object at point A? Okay. So Hiro seemingly got some idea about it. Good. So yeah, it's the ground. I mean, no, I'm where I used to stand. Okay, here's me. Hi. Tell me, Abhishan, what is the gravitational potential energy at point A? Okay. So Abhishan says it's zero. Answer is zero. And Hiroshi also first said it is zero, and then later he changed his mind. Good. So here it is not zero. Okay. It is not zero. So here the gravitational potential energy is not zero. Okay. It has some potential energy. Because now, for example, if you dig a well, for example, let's say uh, you dig a well underneath, okay, what will happen? So if you dig a well, the ball will fall. That means it has a here large potential, here less potential. Okay. So that means here have some potential. It is not zero here. Okay. And in fact, in gravitation field lesson, you will study how to find the gravitation potential of a given point, Kela. But here, what we are finding is actually the relative change in the potential energy. Okay. So here, mgh. Now, the potential energy at point B is mgh. Here, the energy. Okay. Here, energy is mgh. This is actually relative to ground. To this point, the relative to point A, the B point has additional mgh energy. Okay. Now, for example, here energy, let's say at A it is E naught, then at B it will be, so at A it is E naught, then B it will be E naught plus mgh. Okay. Okay. So that's one thing that you should understand. But in this, throughout this lesson, we don't consider this energy. We always consider this mgh, and also we take this as the, we can say this is the, we can come to this reference, or we can keep this reference as gravitational potential energy Gp equals 0. So we are taking as a reference. If we say that this is 0, then here it will be mgh straight away. Because if E naught is 0, then you can see B, energy at B will be straight away 0 plus mgh is equals to mgh. Is that clear? Hirosh, Abhyushani? Okay, good. Okay, so that is potential energy. Potential energy is E equals mgh. Okay. Okay, so I think the next topic that I have to discuss is the mechanical potential energy. Yeah. So right on the topic, the mechanical, sorry, not mechanical potential energy, mechanical energy. Yeah, hold on. Yes, it should be mechanical energy of an object. Mechanical energy of an object. Okay, so write down under that. The sum of kinetic energy and sum of kinetic energy and potential energy. Energy of an object is known as its, it means the objects, its mechanical energy. The sum of kinetic energy and potential energy of an object is known as its mechanical energy. If the mechanical energy is E, so E is equals to EK. Kinetic energy plus potential energy. Okay, write this down. Kinetic energy plus potential energy. Here, by the way, here for this, I should write the topic as gravitational potential energy, because there are various types of potential energies there. So, right, gravitational potential energy. Yeah, it should be gravitational potential energy. So the mechanical energy of an object means the sum of its kinetic energy and its potential energy. And in fact, it's the gravitational potential energy. Okay. Okay, and then write down the topic. Mechanical energy, mechanical energy conservation principle. Mechanical energy conservation principle. So the mechanical energy conservation principle states that sum of the kinetic energy and the potential energy of an object is remains constant. Okay, the sum of kinetic energy and the potential energy of an object is remains constant. That is known as the mechanical energy conservation principle. Because when we say mechanical energy, we consider only its kinetic energy and gravitational potential energy. Okay. Okay. So let's write down the sum of kinetic energy, kinetic energy, and potential energy of an object in a closed system. In a closed system is constant. So closed system means there is no any other type of energy transfer. I mean energy transferring. For example, no heat. Okay, like that. No change in heat energy or elastic potential energy. So only the change occurs in kinetic energy and potential energy. Okay. The addition of kinetic energy and potential energy of a closed system is constant. Therefore, you can write here TK, the kinetic energy plus potential energy is a constant. Okay. So therefore, we can state that initial kinetic energy plus initial potential energy is equals to final kinetic energy plus final potential energy. Okay. We can see an example. For example, let's say we have a ball at some height. Let's say its mass is 2 kilogram. So okay, so this ground, and let's consider the height is something like 10 meters. So initially it's dropped at rest, u equals 0. Okay. So the question is, what is the velocity of the ball when it's hits the ground? Okay. What is the velocity of the ball when it hits the ground, or just before it hits the ground? Say find the v. Okay, so I'll indicate here v is so v is the final velocity. Okay. So now if you get this, we know we can use the equation of motion because it's vertical motion under gravity. So g is 10 meters per second squared. So then I'll do this first using that equation of motion. What we had to do, we had to apply vertically downward. V squared is equals to u squared plus 2as. So final velocity squared, v squared is equals to u is 0 plus 2 into a is g. Height is, let's say, h. So 2gh. So therefore, v equals 2gh square root. So now this one we can obtain by using energy conservation. Okay, so here I can consider this as the GPE 0 level. So I assume in this level, G gravitation potential energy is 0. Okay, so it's actually a reference point. We relative to here, it has some potential energy. Okay, so then we can write the initial kinetic energy is 0 plus initial potential energy mgh is equals to final kinetic energy half mv squared plus the final potential energy is 0. So then here we get m and m cancel, 2gh equals v square, therefore v equals 2gh square root. Okay. Therefore, for this given question, we can find v is 2 into 10 into h is 10, or else I'll make it as 20 meters, so we can take the simplify easy square root. So v equals 400 square root 2 into 2 400 square root 20 meters per second. Okay, all right. You can write this down. I think you might have already done such questions in your O levels, isn't it? Let me know in the chat box because I haven't seen O level syllabus. But when I was studying, it was there for our O level. I think so. Seems like you have done your O levels like. Yeah, so here you can simply use 0 plus mgh equals to half mv squared. Or simply you can even use, without writing the zero terms, you can simply write mgh equals to half mv squared. So this mgh is actually the work done by the gravitation field. Force times the force acting on this is mg, no? So mg, right? And the displacement is h. So the work done is stored as kinetic energy. That's a work energy principle. Okay. Are you done? Why suddenly such a question? No, no, I didn't do. I mean, when during our syllabus, I mean, when I was studying, it was there. Okay, that's what I mean. Okay, okay, I know that. Okay, raise your hand or let me know if you're done writing. Okay, so then we wrote mechanical energy conservation principle. Now we can write the energy conservation principle. That is for all the type of energy. So write down the topic energy conservation principle. So the energy conservation principle says the total energy of a closed system is a constant. Okay. A closed system means you don't bring energy from somewhere. Okay. Okay. Now, for example, you are taking a laser light and radiating to a, like, for example, let's say we have a closed system like a cold container. Okay. So you are laser hitting by the laser light. So then it definitely the laser light carries energy and then it will increase. So such a scenario will not be a closed system. Okay. So closed system means no energy exchange. Now, for example, if you consider this as a room, so there is no energy exchange between the outside and the inside. So that is a closed system. Now, uh, for example, that you know that the regiform box to keep this one. ice cubes. So that one we can consider as a closed system. Okay. Refrigerator, fridge, is it a closed system? The fridge in your home, is it a closed system? No, good. The fridge is not a closed system, right? So in fridge, what happens? We supply energy, no, the electricity. We supply electricity due to this electric energy converts to kinetic energy and it pushes the gas. So that gas compress. So when it compress and expand, the cool down. So when the gas compresses, it absorbs heat, and then again it goes through that coil, and when it expand, no, hold on. When it expand, it absorb the heat, okay, and then when it compress, it release the heat. So something like that. Hold on. When it expanding means it absorb the heat, okay, the gas. So it's absorb the heat, and then when it run through that coil, some the mesh kind of things there, so it will compress. So there it will release the heat, right? So it takes the heat inside and put outside, but by applying a electric energy. Okay, so it is not a closed system. How about the universe that we are living in? The universe, is it a closed system or not? Yeah, the universe we are living in, it's a closed system. Total energy of this universe is, I mean, it is like 90 percentage we can guarantee it's a closed system, but still we can't prove because we don't know the extent, I mean, boundary of the universe, right? No one has ever seen. But we think, I mean, theoretically, as also we think the total energy of the universe is constant. Okay. Now, for example, if I take uh, eraser and let's say I'm rubbing the pencil marks. So my kinetic energy converted to this kinetic energy, and then that kinetic energy also distributed in many ways. Like when I'm vibrating, that air molecules can have some kinetic energy, and then friction it produces heat. So always the total kinetic energy of the universe is constant. Okay, so the total energy of flow system is constant. Okay, so or else we can say the total energy of the universe is constant. That means we cannot create or destroy energy, right? So you can, after writing this, you can put a note. The energy neither created nor destroyed. The energy uh, cannot be created or destroyed. It is always uh, converts from one form to another form. Converts from one form to another. Okay. So that is energy conservation principle. Yeah. So energy can neither be created nor destroyed. Energy may convert from one form to another form. That is energy conservation principle. Okay, to apply conservation of energy, heat losses are usually ignored during the calculation stage. In reality, there are always some energy losses from the system. These should be mentioned when comparing ideal values to real situation. Okay. Now, for example, in a system, if the energy is constant and then applying some input energy and there is some output energy, so the total energy input and total energy output are same, then the system's total energy will remain constant that way also. Okay. There's nothing to like here. Okay, so these and all we had to do questions. We do questions on that. Mechanical energy we wrote. Mechanical energy conservation also we wrote. Okay, so then we'll write about the elastic potential energy. So write down the topic elastic potential energy. Okay. By the way, there is a rotational kinetic energy also there. That part I'm not touching that here. So everything related to the rotation we will discuss in the rotational motion. Okay. Yeah. Now, for example, in a lead translation motion, there is a reluctance we call inertia. So likewise, the rotational motion also have inertia. So everything related to rotational motion we will be studying under rotational motion. Okay, so I'm not going to give that note here. Okay, so potential energy. Okay, so here we state this as a reference point, GPE, gravitational potential energy zero level. Okay, it's for our convenience. Okay, because we don't know exact values, dealing with exact values will be difficult because here the potential value can be something like for example, relative to the ground, uh, it can have some larger value, right? But here, so for example, it can be something around, let's say here, potential energy. I mean, if you calculate, let's say 20,500, or no, even more than that. Okay, so the distance is in kilometers. Not so. For example, Earth radius is 6,400 kilometer. If you convert it to meter, it will be other 10 to the power 3. So then you multiply the mass, let's say 50 kilogram, it will be a huge number. Okay. So we don't do that here. So here we always consider relative to this point how much of energy has increased here. Now here if it goes down means how much is decreased here. If you want, you can take this as the relative GP is 0 as well. That is actually the user's choice. Okay, because still now if I relate it to here, if I consider here, then here it will be less than some difference. Okay, so always because we are taking the difference only always. Did you understand? If you want, if someone want, can take this level as the GP. Is that clear? And calculations will not differ, it will be the same. Okay, I will do one question taking two different GPE values. Okay, now for example, let's say here's a ground and here's a ball is released from rest. The height I take, height let's say 20 meter, for example. (20 meter) and let's say the mass is 1 kilogram. So I'll do this question. Let's say same. I want to find the velocity v. Okay. Okay. So first I consider the GP is here. Okay. Because I think taking here you already know. So I take this as GP is 0. The gravitational potential energy 0 level. Okay. So then I can use kinetic the energy conservation principle using mechanical energy conservation principle. If you want, you can use instead of, you can cut this term also. I mean, without mechanical, you can write using energy conservation principle, because here we are considering a closed system, because and there is no any other way that energy is inserted, or there is no energy input or output from the object or to the object. So therefore, you can write use mechanical energy conservation principle or energy conservation principle. Okay. So the kinetic energy here is 0 plus potential energy here 0 is equals to kinetic energy here half mv squared. Okay, and then we consider here the GP is 0. That means the upward has plus value, down if you put it, it's minus. So then here it has mg minus mgh. So the sum of potential energy. So here the potential energy is minus mgh. So then again you will get v squared equals 2gh. So v equals 2gh square root. Okay, now instead of that, now I'll take another different point. Let's say here in this level 10 meters from the ground. So this one I take as GP is 0. So again I'm using the energy conservation principle. Okay, right. So then here kinetic energy is 0 here at this point, and the potential energy, so here relative to here it is 10 meters high. So I can write okay, so here I get this value in numerical. So v equals 2 into 10 into 20 So square root V equals 40 meters per second. So then here we have, so mass is 1 into, actually mass is irrelevant, mass cancels out. Okay, so m into g is 10 into h is 10 is equals to kinetic energy here half mv squared plus the potential energy here is relative to this, it's minus, so minus 1 into 10 into height is h. So if you take this minus term, it will be plus. So you get here 100, another 100, 200, and there equals half v squared. The mass cancels off. Okay. So here mass is 1. Okay, 1. Okay. So therefore v is again for sorry, here 20. No, this is 20. So again 20 meters per second. Okay. So that is your choice. You can take any pair as GP. The velocity equation, no need to memorize. I mean, this is, you should already know. I mean, almost, you must know this. If an object is released from some height, from here, after some displacement s, its velocity is given by initially drop at 0, u is 0, then v is equals to 2gh. This is, you must know by now. Okay. Yeah. So the GP is actually, I mean, there is no anywhere the gravitational potential energy is 0. We are taking a reference point related to this point. If I say here it's 0, so related to this point we measure. Okay, but normally for this type of question, you can take this point as the GP is 0. But it doesn't matter. You can take any point, but as long as you've done the calculations correctly. If you have any questions, you may ask. Okay, so we want to do elastic potential energy now. Okay, so it can be elastic wire or spring. Okay, so initially F equals 0. Okay, yeah, I will give you the note. Okay, write the topic elastic potential energy. Okay, so let's say we have a spring. So initially we have a spring at its natural length because the applied force is 0. Now force is applied, so here F equals 0, and then so it is in the natural length. So now we apply a force F and extend this. Okay, these horizontal lines I draw because it would be difficult for me to draw by hand using this tab. To guideline only, I draw these horizontal lines. So you no need to write that horizontal line, just draw a spring. And then here if if it's not equals 0, there is a applied force. Okay, so then here's this is the extension. Okay, this change in length, this is x. Okay, so according to Hooke's law, we can obtain Hooke's law. You will study in the 10th unit. According to Hooke's law, this applied force is equals to actually the elastic force. When you apply, there will be an elastic force inside the material. So we just only consider the magnitude of here. Okay, so that is given by F equals kx. Okay, so this is the force. Now we can see if x equals 0, the F will be 0, right? And here k is known as the spring constant. K is known as the spring constant. Spring constant. This spring constant. Okay. All right. Now what we want to find is the elastic potential energy. So when we extend, now for example, if there's a spring and if you are not applying any force, you don't feel any force, right? But if you extend that, you feel it pushes your hand inwards, right? That is due to the elastic force. So there is a elastic potential energy, right? If something attracting means there is a potential energy. Now, for example, this has a potential energy. That's why the gravity is attracting. Okay. So then if you take this one also, it is pulling inwards. If it's pulling towards it means it has a potential energy. Okay. And for example, the electricity also, the electrons flow from higher potential to low potential. Okay. It always tries to minimize the potential energy. Now here, if I drop, it will tries to minimize its potential energy, because when it goes low and below, its potential energy will be decreasing, right? So when I extend this wire, it tries to minimize its potential energy, right? Okay, so in this elastic material, there is a potential energy that is known as elastic potential energy. Okay, so that one we can find using the work energy principle. So I'll try to find the work done when I'm applying a force F to this. So I want to find the work done. Work is, force into displacement. Okay, so the force here, it is not constant. You can see the force is proportional to the extension. Okay, so here I can write the force is proportional to the extension. F is proportional to x, right? That means it's not a constant force, it's a varying force. Therefore, if you want to find the work done, what you have to do, you have to find the work done. So you integrate this force dx, f dx. Okay. In fact, the integration, I think was first the integration was by Leibniz, and Leibniz and Newton. They are the two people who developed the calculus. Newton came from this side, I mean differentiation side, and then Leibniz from the integration side. So they wanted to do this integration to find the gravitational potential. That is the purpose why they developed that. Anyway, yeah. Anyway, so here we can say since f is directly proportional to the x, the force is not constant, it's a varying, right? It varies, right? So you can say this is not a constant force. Okay, so therefore now to find the work done we have to take, now if you integrate that, what you get is for this situation work done is equals to, I don't know whether you have done the integration or not, just I'm saying here, force into dx f dx. So W equals F is Kx, Kx dx. K is a constant, you can take out. So K times integral x dx. So W equals K times, if you integrate x with respect to x, it will be half x squared. So therefore W equals half Kx squared. Okay, so here it comes a half. So therefore in physics we only use its result. We don't uh, do any calculations here. So therefore we say the work done is we take as the average force into, since the force is varying, we take F average into X. So therefore W equals average is initially it's 0 and here it's plus F. So two values mean the average you have to divide by 2 into X. So therefore W equals half Fx. So F equals Kx, so W equals half Kx times X. So W equals half Kx squared. Therefore, the elastic potential energy U, we can write half Kx squared. Okay. So you can write this, or else it is also written as half Fx also you can use. Okay, because instead of the spring constant, if you know the force, you can use this equation. Okay, write this down. If you have any questions, you can ask. Yeah, you can write. You should write all of this. No need to write this part. I'll erase this. Let me know if you finish writing. Yeah, sure. So here, this is the spring is in natural length. That means it doesn't experience any tensile force or compression. No, any compression or tensile. So if you have a rubber band, it'll be in its natural length. Okay. So if you expand only, it will extend, right? So here, no applied force. So it is just in its natural length. And then by applying a force F, you extend to some display extension X. So the relation between force and the displacement can be obtained using the Hooke's law as F equals Kx, where K is spring constant. And you can see this force is not constant. Now we know how to find the work done when an object is moving under constant force, right? We studied if object is there and you apply a force F and it is constant, if it's moved to a displacement of S, then simply W equals Fs. Okay, but here the force is not constant, right? It is varying. So therefore, you have to take the average force. So 0 plus F over 2. So therefore, the work done is equals half kx squared. So then we can consider that work done. When I do a work done, that energy will be stored. Okay, because the energy cannot create or destroyed. So when I do a work, my kinetic energy should change to another form that will be stored as elastic potential energy in the string. And if I release that, what happens? That elastic potential energy converts into kinetic energy. If there is no any friction, the spring will oscillate, but eternally. But there will be friction and air resistance. So therefore, it has to do work against this friction force and drag force and all. So therefore, it will lose kinetic energy because that energy is converting as heat, and this air molecules also absorbing some kinetic energy. Always the total energy is constant. It somehow, if it's losing energy, means it is giving out to other forms, right? Okay. So I think that's all for today. And then in the next class, we have to discuss the power. So power is energy divided by time, or as work done divided by time. Uh, Name the square part again. Okay. You mean this the elastic potential energy. The U, I mean, if you want, you can use the letter capital E for the energy. So this the U, elastic potential energy. For the potential energy, sometimes we often use letter U as well, or V also given for potential. For example, electric potential we give capital V, and gravitation potential also in. It's just a matter of simplification, but this is elastic potential energy. Hirosh, did I answer to your question? The bottom one is same. Now here it's that because we know F equals Kx, right? So U equals half Kx squared, right? That is actually U equals half Kx times x. So Kx is F. So U equals half Fx. So you can use this equation or this equation for elastic potential energy. Yeah. So my bad writing there. Okay. It's F. Okay, so in the next class, we'll discuss what is the power. Power is simply energy over time or the work done over time. And then efficiency, useful energy over total energy input. And then we also have to do questions. I mean, the work done against the drag force, resistive force and all. So yeah, in the next class, we'll 15 minutes or 20 minutes, we'll cover the theory, and then remaining time we'll do questions based on work, energy, and power. All right. All right. If you have any questions, you can ask. Okay. All right. Then good night. Study well. Take care. Next class is on Monday. Yes. Abhishani, our next class is on Monday, day after tomorrow, because we shift swap the classes, paper class and the theory class. Okay. 31st. Maybe 31st is what is the day? Tuesday, no? Tuesday. Is it possible to do one morning? I will let you know. I'm not sure having the class on 31st. And what about you guys? Do you need to have the class on Thursday first? How about Abhi? Okay.